This is an extremely important and subtle definition. You're going to want to pay attention to this. We say that a function f is in big O of x to the n if, in absolute value, f of x is less than some constant times x to the n. Now, we're not saying exactly what that constant is. It's just some constant. And we're just getting an upper bound. We don't actually care about the value of c. We just want to control the growth. Now, there are two versions of this. One, we could say that this inequality has to hold as x goes to 0, in which case big O of x to the n consists of all functions that approach 0 at least as fast as x to the n. On the other hand, if we look at growth as x goes to infinity, then big O of x to the n consists of those functions that approach infinity no faster than x to the n. In both cases, these are an upper bound. This language replaces the higher order terms that we've used in the past. For example, if we look at the expansion of arctan of x, what is that? The first term in the Taylor series is x. All of the other terms are of higher order in x. Specifically, we could say big O of x squared. Or, more specifically, we could say big O of x cubed. That is a stronger statement. It allows us to be more precise. Or, if we want to expand further, we could say that arctan of x is x minus x cubed over 3 plus big O of x to the 5th. Likewise, as x goes to infinity, we could look at a function like x times square root of 5 plus 3x plus x squared. This is a complicated looking function, but really it's just x squared plus some other stuff in the limit as x goes to infinity. That other stuff is itself going to infinity, but only at a linear rate. It is in big O of x. If we wanted to be more specific, we could use the binomial series to say that this function is x squared plus 3/2 x plus something in big O of 1. That is, something bounded, something in big O of x to the 0. More generally, instead of talking about big O of x to the n, we could talk about big O of some other function, g of x, if this same inequality holds for some constant c. Let's look at a few examples. In the limit as x goes to 0, the function 5x plus 3x squared is in big O of x, but it's not in big O of x squared. Sine of x is in big O of x, but not in big O of x squared. Log of 1 plus x minus x, as you could see from Taylor expanding, is in big O of x squared, but not in big O of x cubed. 1 minus cosine of x is in big O of x to the 4th, but not in big O of x to the 5th. Square root of x is not in big O of x to the n for any n bigger than 1. It does not go to 0 very quickly at all. On the other hand, e to the minus 1 over x squared is very quickly going to 0. It's in big O of x to the n for all positive n. As x is going to infinity, we have a number of interesting examples as well. Arctan of x is in big O of 1. It's bounded. That means it's also in big O of x to the n for any positive n. X times square root of 1 plus x squared grows quadratically at most, but it is not in big O of x to the 3/2. The log of the hyperbolic sine of x, well, is really in big O of x. It's got linear growth at most. It's not in big O of log of x. It grows too fast for that. Hyperbolic cosine of x is in big O of e to the x. It has exponential growth, but not polynomial growth. Log of x to the fifth can be simplified, and we see that it's really in big O of log x, as well as big O of x to the n for any positive n. Lastly, x to the x is not in big O of constant to the x for any constant, and it's not in big O of x factorial. This is even superfactorial growth. Now, there's a huge subject of asymptotic analysis associated with big O. It has certain rules. The ones that you need to know for this course are the following. If you take something in big O of x to the m and multiply it by something in big O of x to the n, you're going to get something in big O of x to the m plus n, just like multiplying monomials together. This is true whether you're going to 0 or infinity. On the other hand, if you add two functions together, something that has x to the m growth and something that has x to the n growth, then there's a difference. As x goes to 0, your resulting function is in the minimum of m and n. As x goes to infinity, you're looking at big O of x to the maximum of m and n. Let's look at this in the context of an example. As x goes to 0, consider e to the x over 1 minus x. Well, I'm going to write that as the product of two functions. E to the x is 1 plus x plus big O of x squared. Using the geometric series, we see that 1 over 1 minus x is also 1 plus x plus big O of x squared. Now, how do we simplify this? Well, we pretend that everything in sight is just polynomials and multiply them together, even the big O terms. The first term is 1 plus x quantity squared. The next term is 1 plus x times big O of x squared. Of course, we have two copies of that, so we'll put a 2 out in front. And our last term is big O of x squared squared. All right, now how do we deal with multiplying by big O? Well, collect together the first term, and then notice that that x squared is in big O of x squared, so we can forget about it. Next, we have 2 times 1 plus x times big O of x squared. Multiplying that out to 2 times big O of x squared plus x times big O of x squared gives us what? Well, we don't care about constants with big O, so forget about that. And x times big O of x squared is big O of x cubed. Lastly, big O of x squared squared is big O of x to the fourth. Now, as x goes to 0, those higher order terms all fall under big O of x squared, and we get a simplification. If we want to make it more interesting, say raising everything to the power alpha, then we could use the binomial series to say that this is 1 plus 2 alpha x plus, well, there's some other terms, but they're all big O of x squared.
This lesson on asymptotics dealt with how to deal with the growth rates of change of a function. And though we're at the end of Chapter 1, this provides a perfect segue into Chapter 2, where we'll codify what we know about rates of change into the notion of a derivative.